Hello. Okay, here we're going to go over a quick review of some of the ideas that we've been exploring in our study of simple harmonic motion. So remember, just to start here, simple harmonic motion was defined as a type of oscillatory motion in which the restoring force increases linearly with displacement from equilibrium. So it's not simple harmonic motion if this restoring force is not linear. So this restoring force, which sometimes we'll put as Fr, let's say, has to be linear or proportional with displacement from equilibrium, which we normally would often use something like x for. In Physics 20 here, we have been looking at two main types of systems that exhibit this type of oscillatory motion. The first of all is of course these mass spring systems, and we're going to take a couple of looks at some examples involving mass spring systems, and then we are going to also be looking at pendulums. So in this first video here, I'll go through this example number 1, in which we have a 4.5 kilogram object that is oscillating back and forth on a 40 Newton per meter horizontal spring up to a maximum of 35 centimeters from its equilibrium position. And there's two things we're asked to determine. We're asked to determine acceleration and velocity of the object when it's at that full 35 centimeters, as well as when it's right at the equilibrium position. So I recommend you take a minute, pause this video, give it a try yourself, and then you can press play and see what I've done. And hopefully we've got the same answer. So here we go. This way, I always like to have a little picture when I am solving physics questions. So we've got our little spring, we've got our mass. Let's put the mass all the way onto the ground here. We've got our spring, we've got our mass. There is no friction, and this wall is not going to move either. Okay, so what do we know? We know that K here is 40 newtons per meter, the spring constant. We know that the object is oscillating up to 35 centimeters from its equilibrium position. So if we assume this is its equilibrium position right here, then it's going to be oscillating up to 35 centimeters away, and we'll call that x. It's also going to be going backwards, that same 35 centimeters. It's going to be moving back and forth. And so we know that x here is going to be 0.35 meters. I'll just convert to meters right away since we're going to have to do that at some point anyways. What else we know? We know the mass. The mass is 4.5 kilograms. Okay, so for part A here, we want to find the acceleration and the velocity of the object at 35 centimeters. So for part A, we're asking what happens when this object is way out here at the end and the spring is stretched out. So first thing that we can say right away, we're looking for the velocity here. The velocity here is going to have to be 0. If the velocity was bigger than 0, then the object would be oscillating even further than the 35 centimeters. So by saying that's the maximum, we know that the object has actually stopped at that point. So first part, nice and easy. Our velocity is going to be 0. The acceleration is going to be a little bit trickier to figure out. And to do this, I'm going to draw myself a free body diagram. So let's see what forces we've got. Well, we've always got a force of gravity. It's resting on the surface, so we've got a normal force. And then because we are assuming it's stretched out here to the right, that means we've got a restoring force back to the left. Maybe let's call this a spring force instead, actually. The force of the spring is pulling it back. So in this case, we're only going to worry about our forces in the x direction. Let's assume that our normal force and our force of gravity balance out. We're not worrying about friction or anything. So our net forces in the x direction are just going to be equal to that restoring force from the spring. Remember, the restoring force from the spring can be calculated as the spring constant multiplied by the distance that it's been stretched from equilibrium, and our net force is always going to be mass times acceleration. So perfect, now we've found a way to include acceleration in the calculation here. So all we have to do is solve for acceleration. We can divide both sides by mass, and we find that acceleration is equal to kx over m, which is equal to, we said this was 40 newtons per meter multiplied by 0.35 meters divided by our mass, which was 4.5 kilograms. And that gives us a total of 3.1 meters per second squared. We weren't given any directions in the initial question, so this acceleration we could say is towards equilibrium if we want to be complete. So for question A, we found our velocity was 0, our acceleration was 3.1 meters per second squared. Let me give myself a little bit more room here. Okay, for part B, in this case, the object is actually been moved all the way back to the equilibrium position, so right where it sort of would naturally come to rest, but it is going to be moving. So at this point, our acceleration this time is going to be the easy one to calculate. So our acceleration at that equilibrium position is going to have to be 0 because we aren't going to have any restoring force from the spring acting on it, because our distance from equilibrium is also going to be 0. So by definition, our acceleration also has to be 0 at that point. We can still calculate our velocity though. And anytime in this type of question where you're looking for a velocity, you're going to be going to conservation of energy. So the amount of energy that this system has when it's fully stretched out has to be the same as the amount of energy it has at the equilibrium position. So our way of writing that, we could say that the energy of the spring when it's fully stretched out has to be equal to the kinetic energy that we have at the equilibrium position. So if we recall, the energy for the spring can be calculated as 1/2 kx squared, and that's going to be equal to 1/2 mv squared. So now all we have to do is isolate for v here. So our 1/2s are going to cancel on both sides. Let's divide both sides by m here. Cancel that out here as well. So we have kx squared over m is equal to v squared. We can take the square root of both sides. Let's just change the color here. Square root of both sides, we'll cancel that out. And so we find that our velocity can be calculated as the square root of kx squared over m. If we plug a few numbers in here, the square root of 40 newtons per meter multiplied by 0.35 meters squared divided by 4.5 kilograms. And we find that our final velocity, our maximum velocity here, which occurs right at equilibrium, is just going to be 1.04 meters per second. Again, We aren't going to worry about direction too much on this one since we weren't given any directions to begin with.